Welcome to session on Davisson Germer Experiment. This is the first experimental evidence for the verification of matter weights. Let us see the experimental arrangement. It consists of a low tension battery LT, and this low tension battery is connected to a filament F. D1, D2 are two narrow slits which are made up of aluminium. This is the aluminum cylinder A, and it is connected to a positive terminal of the high tension battery HT. And this is the nickel crystal N, and it is connected to a handle H. By using the handle H, we can rotate the nickel crystal. And this is the Faraday cylinder, which can collect the scattered electrons. And this is the graduated circular scale S. And this is a wire, and this is a galvanometer, sensitive galvanometer G. Let us discuss working. When the filament F is heated with the help of low tension battery LT, electrons are emitted throughout the length of the filament and produces a broad beam of electrons. This broad beam of electrons will be converted into a narrow beam of electrons by passing through two slits D1 and D2. This narrow beam of electrons, after passing through the aluminum cylinder A, got accelerated because this aluminum cylinder A is connected to the positive terminal of the high tension battery. This accelerated electron beam directly strikes the nickel crystal N, and atoms on the nickel crystal scatters the electrons into various directions. The electrons which are scattered at different angles are collected with the help of a Faraday's cylinder, which is mounted on a graduated circular scale S. This graduated circular scale S is very helpful to calculate the value of scattering angle phi. Scattering angle can be defined as the angle between incident electron beam and scattering electron beam. The entered electron into the Faraday cylinder passes through this wire and grounded. When they passes through this galvanometer, it reduces the current, and the current produced is directly proportional to the number of electrons or intensity of electrons entered into the Faraday's cylinder. A graph is plotted between scattering angle phi and intensity of electrons, and it is observed that a maximum intensity always occurs at a scattering angle of 50 degrees and a potential difference maintained at 54 volts. They thought that the electron might behave as waves and produces this diffraction pattern because this term is very similar to the diffraction pattern produced by the waves. If this is true, if the electron acts as a wave, then the wavelength of the electron can be calculated with the help of Bragg's diffraction formula, which is 2d sin theta is equals to n lambda. Here d is the interplanar spacing for the nickel crystal and it's a fixed value, and theta is the angle of diffraction, and n is the order of the diffraction, and lambda is the wavelength. We can calculate the theta value according to the following theory. If this is the incident electron beam and this is the scattered electron beam, the angle between incident electron beam and scattered electron beam is called as angle of scattering, and it is 50 degrees because we got a pronounced diffraction pattern at phi is equal to 50 degrees. According to the rules of the light, angle of incidence is equal to angle of reflection, and this is the Bragg's plane. If theta is the angle of incidence, then theta is the angle of refraction according to the rules of light. So, theta plus phi plus theta is equal to total angle of 180 degrees because this seems like a half circle. So, half circle is 180 degrees, and this angle is theta, and this angle is phi, which is 50 degrees, and this angle is theta. So, theta plus phi plus theta is equal to 180 degrees. So, 2 theta plus theta is equal to theta, and phi is equal to 50 degrees, that is equal to total angle of 180 degrees. 2 theta is equal to 180 minus 50, which is equals to 130 degrees. So theta is equal to 130 by 2, which is equals to 65 degrees. So we got diffraction angle as 65 degrees. By substituting the value of theta in the Bragg's equation, 2d sin theta is equals to n lambda, we are able to get the wavelength of the electron waves. So, The value of D is 0.0909 nanometer and it is fixed for the nickel crystal, and theta we got just now as 65 degrees. And by taking n is equals to 1, which is the order of the diffraction, so lambda we can get it as 1.648 angstroms. This wavelength which we got according to the Bragg's law is compared with the de Broglie hypothesis. But from de Broglie hypothesis, if the electron acts as a wave, then its wavelength is lambda equal to 12.26 by square root of V, where V is potential difference. Here 12.26 divided by square root of V means 54 volts, because we got that pronounced diffraction pattern at the potential difference of 54 volts and scattering angle of 50 degrees. So by doing calculation, we are able to get the wavelength as 1.668 angstroms. According to de Broglie hypothesis, the wavelength of the matter wave is 1.668 angstroms, and according to the Bragg's law, if electron acts as a wave, then its wavelength is 1.648 angstroms. Both are good agreement with each other. Hence, it proves that the existence of matter waves, which means that the electrons in motion behaves like a wave. This is the de Broglie hypothesis proof.